Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Acoustic Treatments of Heating, Ventilation, Air Conditioning and Refrigeration, HVAC&R Machinery in Australia, an Investigation. My name is Amanda and I will be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Conform Group. Conform Group is Australia's first fully fledged engineering company for HVAC&R platforms, acoustic and architectural screening and roof access systems. Specialised in mounting mechanical equipment, Conform's expert team of in-house engineers and designers consult on requirements for projects, and their engineering services include certifying existing buildings to incorporate the solutions they engineer. Conform design, certify, manufacture, supply and install to project-specific requirements, including retrofits, new builds and upgrades. Today, we will hear from two speakers, followed by a live audience Q&A, and I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Nigel Crowe. With 20 years of experience, Nigel is a founding member and managing director at Conform Group, a family-owned and operated business. Nigel's passion for engineering, innovation and problem-solving has led to the success of the group today. Please welcome Nigel Crowe.
Thank you, Amanda, and thank you all for joining us today. As Amanda said, I'm Nigel Crowe, Managing Director here at Conform Group. It's a pleasure to have the opportunity of speaking with all of you today. Today we just want to go over the issues that airborne mechanical noise present. We've been in this industry for 20 years plus now, and issues that come out of airborne noise from mech have been a problem and also continue to be one. And what we've really tried to achieve is to come up with a product that covers most, if not all, of the issues that are found. Here are some of the examples of acoustic barriers that we've seen on commercial sites throughout the country. Because of the lack of products out there to achieve what is needed, we often see examples like this, things that are put out there to block sound that really aren't approved for the outdoor use area and really aren't going to stand the test of time. So we ask ourselves, well, why is this really allowed to happen? What it boils down to, I think what we find is that there is a certain lack of regulation. Different people have different ideas of what can and can't go out there on roofs. There's really no reference to sound attenuation of mechanical plant and machinery in the Australian standards. There are, however, guidelines that are set out, and this is what we're trying to comply with. So really what it comes down to, one of the main things is the structural engineering. We often see products out on roofs that may tick the box with regards to the acoustic attenuation but simply don't last. Australia has one of the harshest climates, as we know, and it's very important to select the correct products when it comes to what can and can't stand the test of time on a roof. Certain things that we do need to consider, which are extremely important, obviously, is loadings with regards to wind. That is one of the main things. We've seen a lot of systems installed on roofs that simply don't hold up, and as soon as there's a weather event, those systems collapse and fail. There's obviously 1170.4, which is very important one again. So we have to comply with the seismic requirements. The basic rules that we follow when it comes to what is required with a acoustic barrier is surface mass or surface density. That is basically the actual weight of the system and also the height. So we have a noise source, as we can see there. We have a noise receiver, and then in between we have the barrier. So what we're trying to achieve and what we're trying to do to make the acoustic engineers' lives easier is to come up with an off-the-shelf product that can be increased or decreased in terms of the surface density. Airborne noise is obviously something that is becoming increasingly problematic, especially within the cities. And a system that can be taken from a specification sheet, taken from an off-the-shelf product and installed on any roof anywhere is what we're really trying to achieve. There's a lot of challenges. Obviously, it's not quite as easy as it sounds. The slide that we have here illustrates some, obviously not all of those. Starting at the top, the system needs to be able to last for as long as what is required. If it's a new build, this is normally 20 to 25 years. A lot of products that are being put on roofs at the moment don't obviously last that time. So we use our experience and knowledge to provide a system that's going to last at least as long as the roof that it's placed on. Weight is obviously a very important thing. Roofs are not designed to take excessive weight. So we need to provide the noise attenuation required, obviously with the least amount of weight. Understanding of how all of these things come together, that's something that is does take a number of years to actually get the skills to be able to put something onto a roof that's going to be able to achieve all of these things. Airflow, very important. We can't create a well effect. We can't put a piece of mechanical equipment inside a sealed box because it simply won't last. So we need to investigate what is required there. Effectiveness, obviously whatever is put up has got to achieve what is needed. Visual, it's got to look good as well. We don't want to devalue the asset that it's getting put on. Cost, of course, is a big thing. Often these things are not realised until fairly late in the project, so cost is very important. And then, of course, safety. It's got to be easy to put up. It's got to be a lightweight system that can be put up safely, and that also is going to actually stay there. So there's ways that we're trying to approach these challenges. The most effective treatments is what we found is absorptive and also a reflective barrier. So an absorptive material and then also mass. So introduce the system that we've developed and indeed installed in every state of Australia, Acoustic Plus. So the major benefits of the system is that it is an off the shelf system that can be put on roofs, whether it's onto our platforms themselves or into steel platforms, or straight onto the roof itself as a retrofit system. What we're doing here is we creating a cassette that fits into a simple post and rail system. Comes in a various amount of colours, which we'll cover soon. And what we do is we apply steel sheets to the actual cassette itself, so we can increase that as the acoustic engineer needs. So if you need 11 kilograms per metre square, or if you need 24 kilograms per metre square, we can increase and decrease it at will. So this is a system that is, we believe, the first one out there that you can actually increase and decrease as you need. We have off-the-shelf options, so we have option A through to E. As we can see there, the different surface densities. Now, each of these surface densities come with their own transmission loss values, octave band frequencies. So from this and from what you can download, you'd have everything really that you would ever need to actually specify each of these products. Different walls can be different surface densities depending on where your noise source is and depending on where your receiver is. So in terms of things like shopping centres, supermarkets, etc., you'll generally get a noise receiver either on northeast, south or west. That particular wall can be upgraded to suit, whereas the other walls can either be downgraded or can actually be turned into visual barriers or louvers, depending on what is needed. Looking at that from the inside, there's a number of different noise absorbing products we use, one of them being Whisper, which is a sealed air product. Polyester is another common one that we use. We obviously make sure that it again has the warranties that are needed. Polyester base is predominantly made from recycled plastic, so being out in the weather is perfect for it, and it certainly lasts the distance. Polyester is not affected by moisture, so water can pass through it without actually affecting it or breaking it down, being a plastic product. The polyester product that we use currently has an NRC of 0.75. This can also be increased or decreased depending on the needs. Our download specification sheet, which you can get there, really covers everything that we believe the acoustic engineers need. Environmental requirements, fire resistance, etc., etc. Again, we've got to be able to comply with the Building Code of Australia for each of these things. Feel free to download that. We have a standard range of the three most common colours that we do see out in the field. Of course, custom colours obviously can be done as well. Surf mist is probably what 80 to 90% of acoustic barriers on roofs are, because that's what the roof colour is. Just a slide here showing one of the main things with this product is we had to make it very easy to actually install, because when you're out up on a roof in the middle of summer, if you up on a roof with light rain, etc., we need the system to be extremely easy, extremely safe to actually install. So again, it's put together with that post and rail system, and each of those cassettes are then slid in. The rail over the top is fixed into place, and then that obviously once that's done, we provide certification to 1657 from there. Just showing our the finished product there. We obviously have a R&D team. Here within Conform Group, we have structural engineers, we have CAD teams. So anything that is custom, we can put together. A lot of the products that we do send out are very custom, because there are certain noisy pieces of plant that are put on roofs, and often it's very much a last minute thing, how we're going to actually stop the noise from going to the neighbours. So we're very much involved in site visits, site measures, putting together systems that can then go to the acoustic engineer for approval. Again, inside, we've tried to make the framing system as minimal as possible. So you can see there we've got very few braces holding the systems up, so we don't encroach at all on the usable area of the system itself. The system itself is obviously everything comes with a 25-year warranty. Surface mounted platforms, raised platforms, as in rafter mounted platforms, as well. As we said again, the system itself can actually be retrofitted to the roof itself. You see there the different colours whenever we are engaged to provide a solution. We have to be able to provide a solution that matches in with the building itself, that matches in with the existing screens that might be already on the roof. Looking at that system, it's there is a retro-mounted system itself, so it doesn't have to be a new build. It can be any build anywhere. The systems are designed to suit existing, new, both on roofs and also obviously down on the ground. A lot of mechanical equipment is put into car spaces, car parks, concrete floors on the ground, and often the noise that they actually produce is not really thought of until later on. So this is a retrofit system that can really suit any floor, any environment that we may have. This slide just gives a bit of a sense of scale. As we've said before, any roof, any pitch, any weight, anywhere. Acoustic barriers, unfortunately, don't always cap off at a certain height. Sometimes they do have to be extreme heights. This is about a 5 metre high barrier that we see here. So having the in-house engineering and CAD team, we can actually custom design very, very high screens, and also that has to work in with the structural engineering of the building itself. So just like to thank you all for listening, and we would look forward to taking any questions that you may have. Thank you very much.
Thank you, Nigel, for your input. And I'd like to welcome our second speaker, Michael Phillips. Michael is an acoustic engineer suitably qualified as a member of the Australian Acoustical Society. With experience across projects of all sizes and disciplines, Michael is a leading acoustical product expert having conducted research and aiding several prominent Australian manufacturers to improve their acoustical systems, product knowledge, and technical data sheets. With continued exposure to both the professional and academic worlds, Michael is uniquely positioned to apply proven acoustical engineering methods, as well as the latest in theoretical acoustic modelling technologies. Please welcome Michael Phillips.
Thank you. Welcome everyone. The presentation today covers acoustical treatments of HVAC&R machinery in Australia, specifically in relation to acoustic barriers. Now, before we begin, mechanical noise control is complex and has numerous issues to consider. Acoustic barriers are usually combined with other strategies and attenuation methods in acoustic design. Further, if you require more information on duct-borne noise, radiated equipment noise, mechanical vibration, break-in and break-out noise, and terminal end noise, feel free to get in touch with us to discuss your specific needs. Our details are located beneath each slide. Okay, so in today's presentation, the key takeaways will be to develop an understanding of the basics of acoustics in relation to barrier design, how we develop acoustic criteria for HVAC&R, how acoustic barriers work, what to consider when acoustically designing barriers. So we'll first go through a summary of some of the relevant principles of acoustics to consider when applying acoustic barriers. So as you see here, sound is a pressure wave that oscillates above and below an equilibrium point. Sound essentially needs a medium to travel, that being gas, liquid, or a solid. So without a medium, sound cannot exist. For instance, if we were to replace the vacuum of space with air, we would be able to hear the sun at 125 decibels from the surface of the Earth. This is a very loud sound that can cause noise-induced hearing loss with about 18 seconds of exposure. So the graphics here illustrate how sound is transmitted. The speaker below will vibrate the air, causing displacement, then transmitting the sound wave. The moving wave, the blue line there, demonstrates sound as an oscillation above and below the equilibrium point, which, for instance, traveling through air, in this case, is atmospheric pressure. This can also be observed on a guitar string. As you see here, it's a guitar string spiked. We can see the vibration occurring. So we have here amplitude, which represents the amount of displacement, which we measure logarithmically in decibels. So essentially, it's signal strength. And a sound that is 3 decibels higher has twice as much energy. This is where we begin to perceive difference in noise level. So for instance, 50 decibels plus 50 decibels equals 53 decibels. This is a fast way that we can calculate the potential impact that an introduced sound can have on an existing environment. So if we know that the background noise level of an environment is 50 decibels, then introducing a noise source of 50 decibels on top of that would be perceivable, and we would have that 3 dB increase. And we've had studies that have shown that this 3 dB increase is barely perceptible to human ear, which we can still though perceive it, and whereas a change of 5 dB is readily perceptible. This is where you may have observed in some criteria for noise intrusiveness being background noise level plus 5. So humans perceive a sound that is 10 decibels higher as twice as loud. An example being that if we have a 40 decibel background, twice as loud would be 50 decibels. And we perceive 20 decibels as being a dramatic change in noise level. Just want to note as well that amplitude is not loudness. Loudness is the human subjective perception of sound pressure. So this means that we can have high amplitudes at different frequencies and may not, as humans, perceive them to be loud. This is something that we factor in when considering what noise and acoustics to essentially to mitigate and whatnot. And this is why we have A-weighted noise levels, which is essentially a filter that filters out very high and very low sounds that humans may not be able to perceive. So what frequency is? Frequency refers to the number of cycles of a periodic wave per second, essentially each vibration, and is measured in hertz. And it's generally accepted that humans can hear frequencies ranging from about 20 hertz to 20,000 hertz or 20 kilohertz. So for instance, in relation to the number of cycles, 1 hertz is equal to 1 cycle per second, with 200 hertz equal to 200 cycles per second. And we have the human ear is most sensitive in the sound frequency range 1000 hertz to 4000 hertz. Wavelength is the distance that a sound wave takes to complete a cycle. High frequencies have shorter wavelengths and use more energy to travel than low frequencies. This means that high frequency sound waves are more easily controlled. And as well, an example is that high frequencies are very small in size. So for instance, 20 kilohertz is equal to 1.72 centimeters. And one cycle of 20 hertz has a wavelength of 17.2 meters. So comparatively, a 1000 hertz signal would complete over 50 cycles over the same distance. And that being, low frequencies have longer wavelengths and thus are more difficult to control. So what this means for us practically with barrier design is that we would need heavier and thicker solid materials to effectively block low frequencies, and not so much with the high frequencies. So an important distinction to make here is that the difference between sound power and sound pressure level. You may have heard the two being used before. So sound power is the amount of acoustical power a source radiates. So essentially this is what HVAC&R equipment generates. And sound pressure is how loud the sound is perceived to be at a specific location. So this can be a noise-sensitive receiver, such as a residential property or nearby commercial premises. When we're assessing for mechanical noise, it is much more useful to know the amount of sound power produced by a source than to know the sound pressure measured, as any measured sound pressures will factor in the environment. Constant sound pressure will produce different sound pressure levels when placed in different environments. So as a result, it's preferred to obtain sound power ratings of potential noise sources during the design stage. So we need to take this into account when calculating noise levels and specifying a solution. Also, as well, it's important to know that sound will die out over distance. So essentially, if we have a doubling of distance from a source, we can get a -6 dB reduction in sound pressure level. So the takeaways that we have here, sound dies out over distance. Lower frequencies are more difficult to control. When specifying sound criteria for HVAC equipment, refer to sound power level, not sound pressure level. 3 dB is a perceivable change. 5 dB is readily perceivable. 10 dB is perceived as twice as loud. Doubling the sound power is equal to +3 dB, and doubling the distance from a source equals -6 decibels. Okay, so talk a little bit now how we develop the noise criteria for HVAC&R. So this is usually dictated by local councils. The reason that it's there is to ensure that noise levels at the nearest noise sensitive receivers are reasonable and undisturbed by any potential intrusive noise sources. Typical criteria that we would see is background noise +5 decibels. And we now know that 5 decibels is readily perceptible noise, which we could consider to be reasonable. So we establish the background noise levels through detailed site-specific assessments. This is what we do as acoustic consultants. This usually entail setting up unattended long-term noise logging for 7 days. This helps us gain an understanding of the existing environment and the typical background noise levels in the area. When we're doing this, we do need good weather conditions and typical activities that are representative of the area. So once we have the background noise levels, we're then able to divide it into relevant time periods. So this is dependent on the use of the noise sensitive receiver. For instance, a commercial receiver may not be in operation during certain hours, as to which we wouldn't need to develop criteria for, and that can have an impact on the time period criteria. So the example that we have here on the screen is a typical residential receiver criteria, where we'd have to factor in 24 hours divided into the day, evening, and nighttime periods. So these periods are relevant, as we'd usually see differing background noise levels during each time. So for instance, the daytime period would typically be louder than the evening and the nighttime periods. So this means that as we have differing background noise levels for that time, it would actually have differing criteria. So you see there to the right with a typical criteria of background +5. If we had a 60 decibel in the daytime, the background +5 would be 65 decibel criteria. And then in the evening, if we had a 55 decibel background, then we'll look at a 60 decibel criteria, which would be background +5. So we need to factor that into the design and management of any noise sources. So we have there as well as nighttime criteria are usually a little bit different. It's dictated by most councils, where they'll, for a residential example, they would expect inaudible within any habitable spaces, which can change the way that we calculate that. So back onto acoustic barriers now. So the primary function of a noise barrier is to shield a noise sensitive receiver from excessive noise sources. And and some of the noise is diffracted over the barrier, which means that the noise bends around the object that you place in front of it. What's the first and foremost thing that we look at is breaking the line of sight, and that's where any barrier attenuation occurs. And with effective barrier design, if we factor in everything that we need to, noise reduction levels of up to 10 dB can usually be achieved with acoustic barriers. So the illustration here shows what happens to a noise source when a barrier is placed between the source and the receiver. You can see that the original path from the source to the receiver is interrupted by the noise barrier. So the receiver, though, is still expected to be exposed to the transmitted and diffracted noise. So we can see there that the diffracted noise, the diffracted path goes over the barrier and then bends around, and then the noise source transmitted path can still go through the barrier. Now, that noise is blocked determined on the transmission loss values of the particular barrier. So we need to know the noise cancellation, reduction properties of the barrier in order to determine whether that it's sufficient to block enough of that transmitted path. So in order for it to be effective, these are things like adequate thickness, density, and height relative to the sound that we wish to attenuate. So further design considerations, noise reduction is greater when the barrier where facing the noise source is lined with sound absorbing material, or a higher barrier extension is required. So if we're able to absorb the noise from that first reflection point of the barrier, we can actually reduce the height of the barrier in order for it to be effective. And you'd also have to ensure that for the barrier to be completely effective, sound leaks mustn't be present. So things like due to holes, slits, or cracks or gaps, or underneath the noise barrier, because at these points we can significantly reduce the barrier's performance to zero transmission loss. And we see that represented here in this illustration. We would have a sound absorber lined to the inner wall of the barrier, and then we can avoid that extended barrier height. So the required output specifications of acoustic barriers, what we would need when specifying a barrier. So these would be the properties required. Be transmission loss, and we need that in the octave band frequencies, which is displayed here with the example acoustic barrier in that first table there. And essentially what the octave band frequencies are, it's a way to make the data more manageable. It's essentially HVAC&R systems can produce noises between 45 hertz to 11,200 hertz. So what we do is, rather than looking at each frequency over 11,000, essentially we group it into what we call octave bands, which are the center frequencies at 63 up to 8,000 hertz that you can see in the table there. So for example, sounds that occur at the frequencies between 90 hertz and 180 hertz are grouped together in the 125 hertz octave band. Okay, so next we have the absorption coefficient is important for us to know as well. So that refers to the acoustic absorber that would usually be on the inside of the barrier. And the metric that we use there is the noise reduction coefficient, which essentially is a single digit value between 0 and 1 that describes a material's ability to absorb sound. So a 0.75 NRC would suggest that it's absorbing 75% of the sound, and we'd usually consider this to be a minimum absorptive recommendation for the inner lining of a barrier. And you would also need the barrier geometry and density, which would be, so we'd look at the thickness and the potential heights of the barrier, and then our density in kilograms per meters squared. So an example product that I've had many clients of mine request that I add to the specification is the Conform Group Acoustic Plus barrier, which I'm happy to work with. Essentially, for me as an acoustic consultant, Conform is able to provide me with the required output specifications. Essentially, they've got a modular system here that I can have input into the density and the absorption coefficient and the height of the barrier. So that works for me, and it's worked for several of my clients as well, which has been quite helpful. So some rules of thumb. What we're looking at when designing a barrier to block noise sources is we want to break line of sight between the source and the receiver. That's something we must do. An acoustic barrier should be placed as close as possible to either the noise source or the receiver. There should not be any gaps in the barrier that can leak noise. The surface density of the barrier must be at least 10 kilograms meters squared. This is relative to the types of frequencies that would usually be blocking with an acoustic barrier. The length of the barrier should be at least 5 times its height, and sound absorptive material is an effective way to reduce barrier height. So that concludes the presentation. Interested in any questions that you may have, please feel free to direct them to the moderator, and I'll be happy to answer. Thank you for attending.
Thank you. A big thank you to Michael and Nigel for 2 great presentations looking at the acoustic treatment of HVAC&R machinery in Australia, an investigation. It's now your turn to get involved, and how to do that is to please send questions through via the chat box. And if you could say who you directed your question to, that would be helpful. A big thank you also to everyone who submitted questions through the registration process. And we might start there. We have a question, and this question is for you, Nigel. And it is, we have a project that requires a barrier equal to RW38. Does your Acoustic Plus system accommodate levels this high? Nigel.
Thank you very much, Amanda. And yes, absolutely. And yeah, this is exactly why we have developed a system that can accommodate really a very vast range. With what we're speaking about here, every scenario is quite unique in itself, and a off of the shelf system needs to be very fluid. It needs to be able to accommodate really everything is needed in terms of surface density. So it needs to be able to increase and also decrease as it's required. So obviously a lot of experience, a lot of research, a lot of technology has been put into ensuring that we do just just that. So in this case, that's that particular RW of 38 that you mentioned. We certainly do have a solution for that, and our 5 different off-the-shelf solutions, option A through E. E would achieve that being an RW of 40, and also having a surface mass of around 30 kilograms per metre square.
Thanks, Nigel. Thank you for that. And Michael, bringing you in now, we've had a great question from Ben, who's watching from New South Wales. Good afternoon to you. Michael, if a project doesn't have an acoustic consultant, are there some good rules of thumb for when treatment will be needed and how much? Michael.
Yeah, thank you. Yeah, very, very good question. What we find though is in most cases where noise control is required, there will certainly be an acoustic consultant required at some stage. So what it's best to do at that point is look at the criteria that you need to comply to, and essentially you need to be engaging your acoustic consultant to do that work, because when we want to reduce the noise, it's usually for a reason to protect the noise sensitive receivers. So in terms of rules of thumb, the ones that were brought up in the presentation, they're the ones that we certainly use, but yeah, would recommend that in all cases, when you do need to reduce noise, get in touch with an acoustic consultant right away, because it's been many cases. I'm sure Nigel can attest to this as well, that sometimes people use a little bit of guesswork, and down the track they need to either modify what they've done, which can be costly, or they've overdone it. So they've overspecified something again, which is essentially putting in unnecessary treatments. Thank you.
Thanks for that. Thank you. And Nigel, a question again about Acoustic Plus. The question is the Acoustic Plus a cladding that goes onto a structure provided by others, or is the structural frame included in this system? Nigel, your thoughts?
Yeah, thanks. So it is really both. Acoustic Plus itself is really a ground-up system, complete with structural frames, connection details to whatever medium we're actually connecting to, etc. Predominantly, we're really do the whole thing from the ground up. Our in-house structural team look after all of the requirements, and then they really design accordingly to that. We do have our in-house NER, National Engineering Registered structural engineers that can design, sign off on any structure nationwide, and then obviously the full test team of CAD, which can provide things that are required, like shop drawings, photorealistic renders, Revit files, wind modelling, and then the list goes on. So really everything required to specify. And then, of course, we also do have our nationwide installation team. So it's really one company that can take the project all of the way through. And I think it's important to note as well that traditionally noise attenuating walls do come at a high price. They're very, very customized, very, very lengthy times to actually install as well. So we've tried to sort of demystify this and try to really break that mold, you might say. Thanks.
Thank you for that, Nigel. I might just stay with you there to the topic of longevity and moving up the country to Queensland. Good afternoon to Robert. And he's asking you, Nigel, in your view, what materials do you recommend for an acoustic enclosure in an outdoor environment in view of longevity?
Yeah, thanks. So, as Michael said before, what really is needed is a reflective barrier, or the barrier that provides the mass, and then a noise absorptive barrier as well. Now, there's a lot of different products that will do those things. However, what we do need to take into consideration is, will those actually last the distance outside? We've got extreme heat, extreme cold, extreme weather patterns, as we've known of late. And as we said before, we really need to be selecting products that will last that 20 to 25 years, the same time as what the roof itself will last. What we've found is that barriers such as galvanized steel, aluminium, and so on are really best to use. A lot of the times, things like FC sheeting, fibre reinforced concrete sheeting, etc., is specified. Things like that are really very, very difficult to install. They're quite time consuming, but they also require maintenance as well. So generally they patched and painted, and then that needs to be done every sort of year or two after that. So it's quite important to select materials that are pre-coated, either pre-coated steel or powder coated, something that you can really set and forget, really. Thanks.
Thanks, Nigel. Michael, you included this in your presentation. Would you like to add to that?
Certainly, one moment. Sorry, I was just caught up on some of the other questions coming through there.
Okay, well, we can move on to the next question. Michael, staying with you then. We've had a question from Chunya in New South Wales asking you, Michael, how can we utilise these control measures in noise impact assessment? Thanks.
Okay, so thank you. So try and interpret that. So noise impact assessments. So usually commercial premises can require noise impact assessment, in some cases needing a barrier. So in order to utilize them, I guess from the acoustic report point of view, we'll place in a specification, but then from there it's up to the client and the whoever's putting it together, whether that be the builder and the manufacturer, so and supplier of the specified barriers and whatnot. So essentially, you'd need this is suitable for Nigel there. You'd need to have the correct specification data. So in order to implement that correctly, you'd have to have proper data sheets from the manufacturer to ensure that you can put the measures in place. Thank you.
Thank you. Nigel, do you want to comment on that? Further elaborate, or are we okay?
Amanda, yes, I think what Michael says is obviously very, very important, and it is very important to select a product that does have scientific testing behind it as well. There are a lot of things that we see out there that that you might say people have put up in an attempt to try and fix a problem, and really all it does is cause a worse problem. So what Michael says is very, very true. It's when selecting a product, it needs to be something that is does have that backing, and that the acoustic engineers can specify, and they do know that once that is actually installed, it will have the properties to what is stated there. Thanks.
Thanks for that. And just staying with you, Nigel, for now, we've had a great question come in from Ian, who's in Victoria, asking, Nigel, can you discuss the solutions for screening of chiller noise and vibration on the roof of a steel-framed building? Thanks, Ian.
Yes, certainly. That's really two questions, really. The first thing being chillers. We're finding that chillers are becoming larger, and there is also becoming more of them in situations that we see more of in terms of data centres, automated warehouses that they have now for some of the larger supermarkets. So there's a huge amount of that going on roofs, obviously being the best place to put them because they're not taking up any valuable real estate on the ground level. These are very heavy; they're very noisy, but there's a few ways to overcome that. We work on a lot of the major supermarkets, and it comes down to where the actual units are placed themselves as well, and then obviously those barriers, which are very, very critical. So it's not to say that chillers can't go on a roof. They certainly can. In fact, it is the best place for them. But a lot of thought needs to be put into exactly where they're getting placed and what the distances from those chillers to the nearest noise receiver is. On the other question of vibration, which is structure borne. So we have noise borne, and then we have structure borne as well. And the best place to attenuate that noise is really between the unit itself and the floor of the platform or the floor of the stand. So there is a number of different spring type solutions which are out there. And generally with chillers or specifically larger chillers, it is definitely a good idea very early on in the piece to investigate what is needed there between the actual base of the chiller and the floor of the platform itself. Thanks.
Thanks for that. Thank you. And Michael, Vishnu in New South Wales is asking us, how important is acoustics engineering in terms of the working of the machinery in the HVAC industry? Thanks, Michael.
Okay, thank you. Yes, acoustics are very important, obviously, because HVAC machinery can be very loud, and essentially in any case where we need to control noise, it would be acoustic engineering would be quite important, really, again, because it would have to be meeting all the relevant criteria. Because what we find is a lot of our work. We work here on projects of all different sizes, and much of the work that we're doing is HVAC machinery. Essentially, we're doing HVAC machinery every day because it's what you really got to look at is how much noise is coming off what you're working with. You've got things transport noise and patron noise from people, and you look at your mechanical noise, which can be a lot more complex because you do have the airborne and the vibration control that like Nigel was speaking about previously. But it's quite significant because at the end of the day, machinery is making a lot of noise and vibration, and without the calculations that we're putting in place, it'd certainly be a very noisy place. Thank you.
Thanks, Michael. Nigel, interesting question that's come in around proprietary. The question being, does Conform Group only provide a proprietary off-the-shelf system, or can you do highly customised solutions also? Nigel.
Yeah, thanks for that. While we obviously try to concentrate on the proprietary off-the-shelf systems, which the reason for that is obviously to keep costs down, because if we can standardise products that go through manufacturing and products that get sent to site and get installed on site, that obviously keeps down costs. However, having said that, because of the team that we do have here, we can really take on anything, big, small, or otherwise. So we've had a lot of interesting projects through the years, but we lean on our skills and knowledge of from the last 20 years, and we would like to say that there's no there's really no there's really nothing out there that we can't definitely have a look at, and really anything that is needed below, let's say, a solid brick wall or a solid concrete wall. Generally, our systems can do, and if they can't do, we can definitely come up with a custom solution to make that work. Thanks.
Thank you for that. Michael, a question here that has come in this afternoon. Does mass and density best used for low frequency noise, but for high frequency are other characteristics required? Thank you, Michael.
Okay, thank you. Yeah, excellent question. So, as discussed in the presentation, when we're looking to control noise, when we spoke about the wavelength and the size of the sound wave, it's in terms of controlling that noise, it's relative to the mass and densities and other things as well, in terms of how well we can control that noise. So essentially, mass and density will control low frequencies, and if you're controlling low frequencies, you'll be controlling high frequencies. So it's really the same thing. It just depends on how much mass and density you need to control certain frequencies. So you can start with a little bit of mass and density to control the high frequencies, and then as you wish to control more frequencies going into the lower range, then that's when you require more mass and density. So essentially it's the same sort of characteristics, just less of those. Thank you.
Thanks, Michael. Thank you. And a good question's come in from Steve for you about how do you prevent minimize noise breakout through the mesh platform floor? And this one was directed to you, Nigel.
Yeah, thank you very much. That's another question that comes up very, very frequently, actually. The job of the acoustic engineer is obviously to minimise the noise coming out of a plant room or a plant deck. But something that's very important that we do need to take into account is the workings of the actual mechanical equipment itself. Now, generally, air conditioning systems, chillers, etc., do require a lot of airflow. Now, if we close up all of the walls and if we bring the barriers right down to the roof in order to minimise noise escaping through the open mesh at the bottom, then what happens is we create a well effect, and that well effect minimises the life of that mechanical equipment, because instead of the air coming in and exiting like it should for the machine to work, it actually circulates within the well. So the air that's coming out of the machine is also the air that's going into the machine, and that actually breaks it down very quickly over time. So it's very important to obviously attenuate the noise, but then give the machine itself enough to breathe so it can actually function right. The way to overcome that a lot of the time is to bring that noise barrier all the way down to the roof or all the way down to the concrete floor, depending on what you want, and then open up any other areas that you can. So Areas where the noise is not critical, generally we'll either leave those open and simply put a guardrail there, or we'll install a louver. So if a visual barrier is required, then we'll install a louver, which gives you 100% visual closure, but also gives you 55% open area. If that isn't achievable, then often a solid floor will be put on the actual frame itself, so something like a checker plate of various thicknesses. But one of the most common ways to overcome that is not in the platform itself, but rather in the actual building itself. So often what will happen is a very heavy density either fibre cement or gyprock will be fixed to the underside of the purlins in the actual footprint of that of where the deck is above. That's generally the most cost-effective way, because you don't have to have a hydrophobic material, and that can actually be fixed underneath. So whether you've got a timber truss or a steel frame building, you can bring that mass and density in underneath the roof itself instead of on top. So there's a number of different ways to get around that. Whatever solution is selected of the ones I've mentioned, we need to be very acutely aware that we don't want to stifle the machines of air that they need. Thanks.
Thanks for that, Nigel. And we've had a sort of a question, more of a statement, so I'll let you put this into the context you'd like to, around wind rating. And that came in from Trinity. Nigel.
So wind rating is something that is very critical, that has to be looked at on every project. And of course, that's run past our structural engineers here in-house. We obviously, our off-of-the-shelf systems are all rated to wind zones A, and in some cases B, that we have here in Australia. C and D are generally custom rated, because then you're looking at your cyclone areas, Far North Queensland, Northern Western Australia, etc. And so those are really looked at as a case by case. But each building is different too, depending on what the building is classed as, and depending on the height of the building itself. The wind speeds change with every project. So that's something that we look at very, very carefully. Thanks.
Thanks for that. Michael, did you want to comment?
I don't know, that's okay. He's got that covered.
Okay, well, we'll stay with you anyway. We've had a question coming from Tafara asking you, how do you minimise or prevent noise from breakthrough windows? Michael.
Good question again. So what we need to look at is usually windows connected to more than just the window. It might be a part of a wall or ceiling area. So we need to actually consider the entire system, so what the window is built into. So hopefully it's built into masonry construction. Then that means we can essentially beef up the window, the acoustical weak point, which is the window, to prevent noise from going from one side to the other, or vice versa. So this is something that we do a lot, really, because windows are a definite acoustic weak point. Obviously you need them for visual transfer at times, but we can do things like providing that we do have a strong system overall, say masonry construction. We can do things like secondary glazing or increasing the glazing thickness, but how we do that is we essentially calculate the noise source, and then we work out how much of that noise source is passing through the window, and then how much additional, glazing we need to put into the existing system. Again, hopefully masonry. If not masonry, we would have to beef up the entire system as an entire barrier, and then we can work out how much extra we need to put in to reduce the noise to the other side. Thank you.
Thanks for that, Michael. And we've had a question coming from Tafara asking you, how do you minimise or prevent noise from going from one side to the other? Michael.
Thank you.
Thank you for that. Nigel, Karim sent in a question talking about the vibration from the machinery itself, and the question is, Nigel, does the fixing method of the post and rail system take into account noise generated by vibration from the machinery itself, in addition to the noise of the motors and fans? Nigel.
Yeah, thank you. So again, that comes down to more of a structure-borne issue there, and structure-borne noise is actually again very critical, and things like noise sickness can occur where the noise is not actually audible. However, the noise is coming down through the structure next to where people are working or sleeping. So these are things that definitely need to be looked at, and often aren't really realised very much until the building's actually built, and then the problem occurs. So the structure of the post and rail system, or the walling system to the platform or to the concrete slab, whatever it needs to go to, does have to obviously be a fixed structure. There's very rarely is there any springs or anything like that provided between the wall bracing and the structure itself. And again, this is where it is it's normally actually provided between the feet or the base of the unit and the flooring that it's sitting on. Thanks.
Thanks, Nigel. A couple of questions come in for you, Michael. First one from William. Good afternoon to you, asking, what programs do you use to assess acoustic analysis for HVAC systems when determining if a attenuator or internal lining is required? Thanks, Michael.
Yeah, thank you. So there's a number of ways to do that. Essentially, what we do here is we use a lot of Microsoft Excel and in-house programs that we've put together in order to do that efficiently. Although there's other programs you can get on the market really. So something like SoundPlan is a common program used by other consultants, but yeah, we're using Microsoft Excel, and essentially all the calculations you can find in the Acoustic academic books. We've worked them into our own systems and built them here. Thank you.
Thank you for that. The second question has come in from Steve, asking, Michael, would you use average background or rating background noise levels to set your HVAC criteria? Thanks, Michael.
Yeah, good question. So we use the rating background level, which is the RBL. So essentially, we're taking the medians over the assessment period. So as we talked about in the presentation, the day, evening, and nighttime levels, the medians over those time periods of the entire assessment period. So say, for instance, if it were a 7-day noise monitor, we'll consider that the assessment period and take those medians at the time period, and then obtain the RVL, which would be for the L90, which is 90% of the noise level throughout a particular period. And then we'll use that to set the HVAC criteria. Thank you.
Thanks, Michael. And staying with you, Michael, and sort of circling back to your presentation, we've had a question come in asking you, on an acoustic barrier, you mentioned NRC of 0.75. Is that 75% reduction for each octave grouping, as per your slide? Michael.
Yep, good question. Thank you. So what NRC is, it's an average of the middle frequencies to the nearest 5% to get a single digit rating. So it's not 0.75 at each octave grouping. So in an ideal world, it would be 0.75 across the spectrum would certainly make it easier for us to specify single-digit ratings. But essentially, it is an average across a number of frequencies, which can pose some issues when specifying single-digit values on account of that. So I can see why you would ask that question, but it's not across each part of the octave band. It is a single-digit rating average across the octave band. Thank you.
Thanks, Michael. And before I bring Nigel back in, another question for you asking, what's the mechanism for the absorptive liner reducing the barrier height? Is it just reducing noise buildup? Thanks, Michael.
Yeah, very, very good question. So it's not. It's usually a porous absorber, so it's not blocking sound. It is certainly reducing what we call reverberant noise. So you might think of this if you're in a very reverberant hall or an atrium or somewhere where it's a lot of reverberant noise and lots of echoes, you might notice that it can feel quite noisy, but the noise we refer to as reverberant noise. And then once you can start minimizing those reflections, you might notice that things seem a bit quieter. So if you're in an office with good essentially absorptive ceiling tiles and carpet and maybe some acoustic treatment on the walls, you might notice that things they feel quieter, and they are actually quieter. So as much as reverberation is echoes, it's still the sound over the sound frequencies overlap each other, and then they can reinforce and create greater sound pressure levels at different spaces. So it's certainly reducing the reverberation time, which then if you look at the noise source of say on the barrier and then all the mechanical units inside, once you've reduced the reverberant noise, all of the noise that's coming out from that particular area would then therefore be reduced, because if you look at it all as a source, then with less reverberation, less noise would then be transferred to your nearby receivers. Thank you.
Thanks. Nigel, coming back to you, and we are running out of time. I just want to talk about, we've had a question that the system looks like it's made from a common post and rail system. Can this be used in other instances other than mechanical plant platforms? Nigel, your thoughts?
Yeah, thank you. Yeah, certainly, and yes, that certainly is correct. And we are very passionate about keeping things as simple as we possibly can. So what we have done with the standard systems, well, all of our standard systems really is they all based in a very common post and rail system. This makes them not only cost effective, but again incredibly quick to actually put up on a site. And whilst the system itself is very effective as a rooftop barrier, the uses are really endless for it, because it's been designed to go in a common post and rail system. Now, by common post and rail system, that's really very similar to the barriers between houses, etc. So it's quite vast, the uses that it can do, because the actual panels itself, and if you go to the website, you'll see a bit of a breakdown as well as what we covered previously of how the system actually works, and the cassettes that we actually manufacture here. They are all 100% compatible with the residential post and rail boundary fences, as we've said. So if there's issues there, as we know, the standard post and rail type fences aren't great at really blocking noise. So if there are noise issues, which there really are a lot, in between houses or between residential and commercial or pet noises, etc. Normally, where there is a problem, that existing post and rail fence will be taken down to make way for a brick or a concrete wall. But what this means is that you would need to obviously replace your fence entirely, coming at a cost. But in this situation, with the cassettes that we have developed, they're actually the same width as the steel sheet that normally goes in. So instead of actually replacing the entire wall, what can happen is that only the actual sheet itself is actually replaced with those Acoustic Plus cassettes. And again, you can increase or decrease the density to what is needed. So obviously, this does come at a massive save. So there is a lot of save in time and cost there as well. So whilst we've been mostly talking about attenuating mechanical equipment on roofs, the system itself has a huge range of other uses itself. So particularly in the one that I've just said. So you might be able to say goodbye to your noisy neighbours at last. Thanks.
Thank you. That would be welcome. Just before we close today, we've talked about thought leadership in acoustic treatments of the machinery. I'd just like, on behalf of Engineers Australia, to ask you both, starting with you, Michael, as to what advice would you give to our young engineers that are looking at entering into this sector, into this field? And I've deliberately kept that broad. Michael.
Okay. Yeah, sure thing. No worries. Well, yeah, it's. I think for me personally, it's. I'm very. I've come from a musical background, so with acoustics, there's certainly a passion. So, I would say you have to enjoy what you do. And listen to the elders in the industry. So whenever I can, because I'm not I can't have 50 years in this. I'm not 50 years old. So whenever I can, and I'm speaking to the older people in the industry, I just pick their brains and learn. So I'd say learn as much as you can from as many people as you can, because it's a engineering, all fields, but in acoustics I can speak for specifically. It's a dense subject. It's really interesting, and as long as you love it and keep asking questions and learn from as many people as you can, it works out from what I've seen. Thank you.
Thanks. Wonderful advice, Michael. Nigel, bring us home.
Thanks. Yeah, look, I couldn't say as much as Michael, certainly to a lesser extent, but what we can say, I guess, from day-to-day experience is that there is a lack of professional people, professional advice within the building industry out there, and that's only getting less. So there definitely is a need for that, and as we're seeing with Australia itself trying to increase the viability of building itself and trying to build better, trying to build safer, trying to reduce noise pollution, trying to have greener cities, etc. There definitely is a large need for these people, these trades, these professions that you can draw on. So I'd say, don't hold it out there, something that you can't achieve. There certainly is a market for it out there, and there certainly is a need for people that can answer these questions, such as Michael. Thanks.
Thank you, Nigel, and thank you for that advice. It is all we have time for today, and I'm sure you'll join me once again in thanking Michael Phillips and Nigel Grove for their time and input. I'd also like to thank Engineers Australia's industry partner, Conform Group, for their support. As always, we do ask you if you could please take a couple of minutes to complete a short feedback form, which is linked in the description box below. Helps us plan future sessions. Thank you again for joining us, and we hope to see you at our next Thought Leaders event. Thank you and good afternoon.